Yeah, I was very much looking forward to participating in person in Bonn. I have very fond memories of my my previous visits there, and of course, I have so many friends in the program. And it's a shame that it's still too difficult to travel for me, but maybe I will hopefully visit sometime during the program. Yeah, so I'll be speaking on a certain further progress in number theory. There's been a lot of progress recently on understanding bounded multiplicative functions. And just to fix ideas, I will focus mostly on the Liouville function, which is a particularly model function of which sort of captures a lot of the progress, but we still don't have everything we want. So I know this audience is mixed, so I will review some standard concepts, starting with what the Liouville function is. So the Liouville function, lambda, is a function of the natural numbers, an arithmetic function. It takes values plus or minus 1, and it's completely multiplicative, which I guess I didn't define what that means. Completely multiplicative means that it's a character, lambda of nm is always equal to lambda of n, lambda of m. That's what it means to be completely multiplicative. Oh, I knew it was a bad idea to use a stylus. Okay. All right. Okay, it's the unique multiplicative function, which is minus 1 at every prime. In other words, lambda 1 is 1, and every time you multiply by a prime, you flip the sign. So therefore, since every number is a product of primes, lambda of n is just 1. It's minus 1, sorry, to the number of prime factors. Okay, so it's 1 when you are a product of even number of primes, and minus 1 when you're product of odd number of primes, counting multiplicity. It's very closely related to another important function in number theory called the Mobius function, mu, and they're very close cousins, and so much so that pretty much almost any theorem you say about lambda has a counterpart for mu and vice versa. But just to fix ideas, I'll just talk about lambda. Okay. All right, here are the first few values of the Liouville function. I mean, it takes plus or minus 1, and there's no really discernible pattern, well, other than the fact that every time you multiply by a prime, it changes sign. But it looks kind of random. And so we can, and there's an informal heuristic that kind of governs that, which is called the Liouville pseudorandomness principle. So this is not a precise statement, but the feeling is that whenever you sort of investigate the Liouville function statistically, it should behave as if it was random. In most, except in sort of, I mean, there are trivial tests to test that it's not. Okay, for example, lambda of 2n is always minus lambda of n, which is not the case for a random sign pattern. But as long as you're not deliberately trying to cheat, any statistical test for the Liouville function should give you the same type of statistics as a typical random function from n to plus or minus 1. There's a more commonly referred to cousin of this principle, which is the Mobius pseudorandomness principle, which I won't discuss here. Okay, so for instance, so what kind of statistical tests can you do to analyze this function? So you can look at averages. Okay, so for example, you can average the Liouville function for all numbers up to x. So I use this averaging notation: e n up to x lambda of n means that you sum all the numbers lambda of n for all n up to x, and then you divide by the total number of numbers less than x, which would be x, for example, if x is an integer. So that's the average of lambda from all the numbers up to n up to x. It turns out that it's easier sometimes to do a smoother average, which I call a logarithmic average, e log of n up to x, where you weight by the harmonic weight. So you sum from n up to x, but you weight each number n by 1 over n, and then the denominator, instead of dividing by x, you sum over the nth harmonic number. You sum over 1 over n from n up to x. So if you like, you're picking a number n randomly from 1 to x, but now with a 1 over n weight, and you're asking for the expected value of lambda of n. And this denominator is roughly log x. That's why we call it a logarithmic average. Okay, so these are smoother averages. If you can control ordinary averages, then there's an easy summation by parts so that you control log averages, but you can't go backwards easily. If you control the log averages, it's very hard to get from there to control ordinary averages. Okay, so all right, so the randomness principle predicts that these averages are very small, and what do we know about them? So if you look at the log averages, there's actually some very easy arguments that okay, I won't show them here, but in half a page you can show that that the log averages decay. In fact, like 1 over log x is not difficult. But the ordinary averages they decay as well, but that is hard, or at least harder. That's as hard as that's equivalent, in fact, to the prime number theorem, showing that the Liouville function has mean 0 is actually one of the equivalent forms of the prime number theorem. That was observed by Landau. And we know we can improve the little one term a bit more. I think exponential of log x to the minus 3/5 or something, roughly. But the conjecture, which is the famous Riemann hypothesis, is equivalent to the statement that you should get square root type decay. That the average value of lambda of n should actually decay like square root of x up to some epsilon errors. Okay, so that's one very simple notion of randomness, just computing the mean. Now, of course, the prime number theorem is usually proved by complex analytic methods, and the starting point often, well, you don't usually start with the Liouville function. You usually start with a cousin like the Mobius function or the Mangold function, but in all the proofs, all the complex analytic proofs, you take your function and you basically take a multiplicative Fourier transform, otherwise better known as a Dirichlet series, and you write that in terms of the zeta function, and then you start investigating things like where the zeros or the zeta function are. Okay, but there are non-complex analytic proofs. Famously, Erdős and Selberg have an elementary proof, and there's a couple other elementary proofs in literature. In fact, just last year, there was 2 simultaneous proofs that were very closely related. One by my student, actually, Redmond McNamara, and then one by Florian Victor, which also gave a proof of the prime number theorem, which I will spend a little bit of time on here, because it's a nice, it serves as illustrating some of the ideas I'll talk about later. And it didn't use Dirichlet series. It relied mostly just on the multiplicativity property. Lambda of Pn is minus lambda of n, but not for all primes p, because that would actually define lambda, but just knowing it for small primes p is actually enough to get the prime number theorem, basically. And I wanted to describe these arguments. They are much weaker in bounds. So the complex methods give the best bounds. There are now actually some pretentious methods that give competitive bounds, but these bounds are really weak, like 1 over log x type bounds. But they are elementary, and they extend to more general context. So let me first start by proving a really unimpressive bound, that if I take the log average of the Liouville function, I will just show that it is literal of 1. Okay, so the trivial bound is 1, because lambda is plus or minus 1, so the triangle inequality is 1. As I said, it is already quite easy by elementary methods in half a page to get 1 over log x. You just do a very short, just Fubini's theorem, basically, double counting. But so I will prove something which is actually worse than the easy bound, but still better than triangle inequality. Okay, so our main tool is for this is a very nice inequality of Elliott from the 70s, and it says the following. So suppose you have some interval I on the integers or on the real numbers of length at least 1, so it contains at least 1 integer, and you take any function you like on this interval, and you study its average, and you but you also study its average on multiples of primes. So so you look at first all the integers inside this interval, but then you sample it. You only take every second integer, or every third integer, or every fifth integer. So for every prime, you look at the elements in your set which divide that prime, which are multiples of that prime, and you take the average of f only on that sub-progression. So that's so sampling this mean. And Elliott's inequality says that actually this sampling, this sub-average is often close to the full average. So it might not be. For example, if f is fluctuates between even numbers and odd numbers, it might be much bigger on odd numbers than on even numbers. So if you average on even multiples of 2, then the average on over multiples of 2 might be quite different from the global average. But then if you instead average over multiples of 3 or multiples of 5, then whatever irregularity you had at multiples of 2 won't show up again. And so while you can have deviation from the mean for some primes p, but it turns out that for most primes p, you don't. At least as long as your primes are kind of small. So if you restrict to primes smaller than, say, I to the 0.1, and if you weight the primes in a certain way, I'm using 1 over p, then on average, in a certain L2 sets, on average, these deviations are small, and they're bounded by actually the L2 norm of your original function. This is not hard to prove. I'm skipping the proof, but it's you basically dualize and use Cauchy-Schwarz, or to analytic number theorists, they call it the large sieve inequality. The key factor you use is, this discrepancy between the global average and the local average is the same thing as the inner product between f and a certain function, which is p times p times the indicator function of the multiples of p minus 1. And the key point is that these functions are almost orthogonal on I. You take the inner products for any two small primes, they're almost 0. And then this is basically like Bessel's inequality. All right. So if you take this inequality for granted, what it says is that roughly speaking, for most primes, the local average is the same as the global average. Although most is, you have to quantify this, and the quantification is not great because this 1 over p sum, it does diverge, but extremely slowly. It's like log. And so when you actually try to put bounds everywhere in this type of argument, you only gain like log factors, which is not great, but it's still non-trivial. Okay, so all right, that's Elliot's inequality. So in particular, if you're averaging a function from n to x up to x, then for most primes p, that's like averaging over multiples of p, which after change of variables is like averaging up to x over p, f of pn. So you get this sort of dilation formula. It's like you can change variables, you can scale by p. So if you had a continuous integral here, if you integrated f from 0 to x, you could change variables and integrate x over p, f of p t dt. For continuous functions, you can change variables. And normally for discrete sums, you can't change variables like with dilation, but Elliot's inequality says that you kind of can, at least for most primes p. But the ranges of integration change. But the nice thing about logarithmic averages is that if you average logarithmically, averaging log x and log x over p are almost the same when p is small. And so actually, for log averages, you don't even need to change the limits of integration. That log averages have this very nice dilation invariance that you can change variables from n to pn, and for most primes p, it doesn't really change the integral. So it's almost as if the log averaging is like a hard measure for dilation, like dt over t is for the positive reals. Okay, so we have this sort of scaling symmetry, and that's what makes log averages really convenient to work with. Okay, so now I can prove a really wimpy version of the prime number theorem, which is that the log averages of the Liouville function decay. So why is that? Well, we can apply Elliot's inequality, and Elliot's inequality tells us that we have a dilation invariance, that if you want to compute this log average, we can dilate, and for most small primes p, we can just change variables n to pn, and we can replace lambda of n by lambda of pn. But on the other hand, the defining property of the Liouville function is that every time you multiply by a prime, you change the sign. So clearly, when you take any average of lambda of pn, that's just the negative of the average of lambda of n. So the average of lambda is approximately the average of lambda of pn, which is equal to negative the average of lambda of n. And you combine the two, that this average has to be roughly 0. Okay, and that is a proof of this very, very weak inequality. Okay, so we can see that Elliot's inequality actually has some use. Now, with a little bit more effort, you can actually get the prime number theorem by this argument as well. What you can do is that you can first iterate. Okay, so when you take ordinary averages, then you still have this sort of scale invariance, but the limits of integration change. But then you can iterate it. So you can divide by prime again and again. And what you find as a consequence of Elliot's inequality is that if you take, say, k small primes, p1 to pk, then if you average lambda up to x over the product of k primes, you apply Elliot's inequality k times, and you apply the sign flipping property of Liouville k times, you find that the average of lambda for k over the product of k primes is about -1 to the k times the average of lambda over the original x. So, okay, but now the limits of integration have changed. So we can't quite argue as before. So you need one more trick to finish. And Victor and McNamara came up with two slightly different tricks. Florian's approach was based on, he used a little bit of additive combinatorics, and he found two numbers, which are products of primes, where one was the product of an even number of primes, and one was the product of an odd number of primes, and they were close together, that he could find two numbers with different parities of prime factors, which were close, and he applied this type of approximation to both of them. And but the thing is that because of the sign change, you could show that all the averages here were basically zero or close to zero. And Redmond McNamara's approach was related. He located a place where this average executes a sign change. So if the prime number thing was false, then this average would be large and positive somewhere and large and negative somewhere else. But it's also kind of continuous in X. So at some point, there has to be a sign change at some capital P. And then by using an elementary formula of Selberg, he could find either a prime or a semi-prime, product of two primes, like close to that P. And using one of those two, plugging it into here, he could get the prime number theorem. Okay, so you need a bit more work when you're dealing with ordinary averages, but you can get at least the prime number theorem from this dilation and variance approach. So this opens up sort of this new type. It's not that new. It's from the 70s, but it's a different way of attacking multiplicative functions from what you might be used to. So that was the prime number theorem, but the same technique can work to prove other things. So, for example, here's a classic estimate of Davenport that if you look at Fourier coefficients of the Liouville function, if you take the Liouville function lambda of n, and you take a Fourier coefficient, so you write use the number theory notation, e theta is the character e to the 2 pi I theta. If you take lambda of n e to minus 2 pi I alpha n, all of these averages are small, and in fact Davenport showed that they decay like any power of log x uniformly in alpha. Okay, now we won't prove that here, but again we will prove a weaker estimate, which is still interesting. We will just prove that these averages actually decay. That they go to zero, but not as fast as log x. The argument I give will only give like a log x type decay. Okay, but again, you can just use Elliot's inequality to conclude. All right, so suppose that we don't have decay. Suppose that this average is big. So by the way, of course, the randomness principle that I mentioned earlier predicts you should have lost a decay. So in fact, we should have like square root decay, but we can't prove that even on GRH. Okay, but all right, but suppose that there's no decay at all. Suppose that this is very large. Then we can use Elliot's inequality, so we can rescale. So we scale by any prime p, and so for most primes p, let's say primes p close to some scale capital P. So for most scales capital P and most primes at that scale, we can dilate, use Elliot's inequality to dilate change variables n to Pn, and so this guy should be large as well. All right, but lambda of Pn by the defining property of the Liouville function is just minus lambda of n. So I can just, and I've got absolute values here. So this tells us that at this slightly smaller scale, x over p, lambda of n, the Fourier coefficient at lambda p, alpha p is also large. Okay, so because of this dilation and variance, once you have a large Fourier coefficient at alpha, you also have a large Fourier coefficient at alpha p at a slightly different scale. But now you have many large Fourier coefficients. And so you can start playing games with that. All right, so we have this large Fourier coefficient. Lambda correlates with e to the alpha Pn. So I'm going to write that in formula. This function lambda has a correlation with this Fourier character here. Now, correlation is not transitive. This is something that we beat into our heads of our statistics students, right? That if A correlates with B and B correlates with C, then A doesn't necessarily correlate with C. But nevertheless, it does happen quite often that if A correlates with B and B correlates with C, then A has a propensity to correlate with C. And when you have lots of correlations, some positive fraction of the correlations are transitive. You can use the Cauchy-Schwarz inequality to justify that. But let's just pretend that correlation is transitive. So if lambda correlated with a lot of different characters, then these characters, they should mostly correlate with each other. So there should be many primes p and p prime. So E of alpha pn and E of alpha, there should be p prime n. They correlate with each other. So all these characters should actually correlate with each other. And that's a good statement because it doesn't involve lambda anymore. And now it just involves Fourier characters. And you can compute what this means. You can compute the correlation by exponential sum estimates. And what you find is that alpha p and alpha p prime have to be close to each other mod 1. Well, actually, you have to pigeonhole a little bit until this is the case. But basically, because you have all this correlation, alpha p and alpha p prime have to be quite close to each other, at least their fractional parts have to be close to each other for many, many primes p. Now, this situation is well understood. There's a classical lemma of Vinogradov. So Vinogradov made an extensive study of the fractional parts of things like alpha p. And he showed that for most alpha, like when alpha is really irrational, the alpha p's are actually equidistributed mod 1. And so, in fact, they are not often very close to each other. They are all over the unit circle. So, in fact, the only way that the multiples of prime alpha p, multiples of alpha, stay close mod 1 is if alpha is almost rational. If alpha is what's called major arc, which means that alpha is almost a rational A over Q, where A and Q are very small, bounded numbers, like if A is close to 1/2 or 2/3, plus an error which is very, very small. So there's a lemma which basically takes this equation and sort of morally divides by P, and you can sort of get rid of the P and just control an alpha. Now, normally you can't do that because there's mod 1 would get in the way, but if you have this is true for all or many primes P and P prime, you can, in some sense, divide by P. Okay, so alpha is then very, very close to A over Q. So then this e to the alpha n that we are correlating with is actually very close to this periodic character, e to the n over Q. And so instead of correlating lambda with this real frequency, e alpha n, we can just correlate with a rational frequency. And we just need to understand the correlation of lambda with this periodic function. And this you can prove using a variant of the prime number theorem. So if you didn't have this rational factor at all, this would be the prime number theorem. And you can use instead what's called the prime number theorem in arithmetic progressions, which is a known theorem. And in fact, you can even adapt to the previous arguments of Richter and Redmond to McNamara to actually also prove this. Well, you still need the non-vanishing Erewhon chi for the experts. I mean, that you can't get rid of. But okay, but anyway, this is a simpler problem that you can solve. All right, so this proves a weak version of Davenport's theorem. Okay, so I should mention, so this arrangement of the argument is new, but similar ideas have been around for a long, long time. Similar ideas using multiplicative via small primes, but arranged in a slightly different way, have appeared the work of Montgomery Vaughan, Debussy-Delange, and then more recently Katai and Bourgain, Sarnak, Ziegler. Yeah, and so the same arguments show that Liouville function doesn't correlate with polynomial phases, Yorke decay, by basically the same argument. And more recently, you can get fancier things. You can also correlate lambda with things like what are called no sequences, and you can show also the correlation decays. And in fact, this argument I gave only gives log-log type decay, but if you use more traditional methods, like Born's identity, you can get decay like any power of log. This was useful because this actually has an important consequence. You can control, you can start counting solutions to linear equations in primes, but that's not the focus of this talk. All right, so that's sort of one direction in which we can understand the randomness of the Liouville function. Another direction people study is to look at sign patterns. Okay, so you can think of the Liouville function as just a sequence of plus and minus ones. So you can look locally. You can look at k consecutive values of your function, and that's called a length k sign pattern. And you can ask how many sign patterns occur in your sequence. So you have a moving window of size k. You look at your sequence, and you look at and there's 2 to the k different possible patterns, but some might not occur in your sequence. For example, if your sequence is all ones, then there's only one sign pattern of length k, just 1, 1, 1, 1, 1. So you can count how many sign patterns occur. So we let SF be for any function f, any sign pattern sequence f. You look S of k be the number of sign patterns of f that occur of length k that occur infinitely often. So that's some number between 1 and 2 to the k. Usually it's 2 to the k. If you take a random sequence, then just by the infinite monkey theorem, every sign pattern appears infinitely often. But there are a few sequences where the sign patterns are much rarer. There are a few sequences called deterministic sequences where the number of sign patterns are sub-exponential. So for example, a periodic sequence would be a very simple example of deterministic sequence, and there's a few others. There's a bunch of conjectures in this regard. So Sarnak in particular made some famous conjectures. So there's the weak one and there's a strong one, and then there's an average version of the strong one, which is in between the weak and the strong conjectures. The weak conjecture says that lambda is not deterministic. So that means the number of sign patterns of lambda should grow exponentially in k. So that's the weak conjecture. The strong conjecture is furthermore, in fact, not only is lambda not deterministic, it's actually orthogonal to all deterministic sequences. In fact, that lambda, if you take any deterministic sequence, for example, then the correlation between lambda and any deterministic sequence should go to 0. And then there's an average version of that, which is that the logged average version of lambda with a deterministic sequence literal of 1. So there's an error. There's a chat. Is the definition, is that a literal O? Yes. Yeah. So deterministic means that the number of sign patterns is less than equally epsilon k for every epsilon for k big enough. Okay. Okay. So these are the Sarnak conjectures. So there's been a lot of work on the strong one in particular. There are many examples of deterministic sequences for which this conjecture has been verified. For sign patterns, I can tell you what's known. The strong conjecture actually implies the number of sign patterns should be 2 to the k. Right? All sign patterns should occur infinitely often. But that's actually only known up to k equals 4. All the sign patterns of length 4 occur infinitely often. For 5, we have some partial bounds. The number of sign patterns of length 5 that occur infinitely often, somewhere between 24 and 32. We have some lower bounds, but not exponential. The best bounds known are in fact basically polynomial. That the number of patterns that occur infinitely often is at least quadratic, and the number of patterns that occur at least once grows faster than polynomial. But we are still quite far from getting exponential growth. So to control sign patterns, actually, most of the recent progress is related to a close relative of the Sarnak conjecture, and this I think is really the central conjecture about the Liouville function in the subject, which is called the Chowla conjecture. And this is really saying that locally the Liouville function is statistically looks random. So what it says is that that if you take any shifts h1 to hk and you compare lambda of n plus h1 up to lambda n plus hk, that the average of any product of lambdas should also be literal of 1. So if you only had one factor, this would be the prime number theorem. And so this is sort of a multi-point version of the prime number theorem. Yeah, and there's a log average version and there's a non-log average version. There's a typo. This log should not be here. Okay, so yeah, so these are really the key conjectures in the subject. The Chowla conjecture implies the log average Chowla conjecture. It's also known that that Chowla implies the Sarnak conjecture, the strong Sarnak conjecture, and the log average Chowla conjecture is in fact equivalent to log average Sarnak conjecture. So there's a lot of equivalences. As a first approximation, all these conjectures are sort of morally the same conjecture.
Terry, there is a question in the chat.
Yes, I answered it. Yeah, there was a little O in the exponent. Okay. All right. So this is the Chowla conjecture that k-point correlations are small. It's kind of a baby version of the Hardy-Lewis prime tuples conjecture for primes. If you replace lowercase lambda with uppercase lambda, you basically, roughly speaking, get the prime tuples conjecture. That's now a main term on the right-hand side as well. So in particular, you can think of even the k equals 2 case is kind of like a baby version of the twin prime conjecture. So you would expect it to be sort of hard. All right, but we've made progress. So for k equals 1, it's the prime number theorem, as I said. For k equals 2, we now have, we can prove the log averaged version of the Chowla conjecture. That I did in 2016. And then very, very recently, there was a nice quantitative refinement with a slightly different method by Helfgott and Radzui. And this particular result actually had a nice application. You could actually solve something called the Erdős discrepancy problem, but that's a topic for another talk. So we can do k equals 1, we can do k equals 2. Because of a parity trick, we can also do all odd k, at least for the log average conjecture, Chowla conjecture. Without the log averaging, it seems to be quite more difficult. But what we can do is that all the results I just said for log averaging, they're also true for the unaveraged Chowla conjecture, but only for almost all scales. We can't yet prove it for all scales, but you can leverage the log averaged conjecture to, or you can modify the proofs a little bit to get the Chowla conjecture, but for almost all x rather than for all x. And then there's some exciting progress in function fields. So, for example, Sauer and Schusterman, when you have a function field over and the base field is a prime power order, p to the j for some large j, then actually they prove a lot of things. They can prove Chowla conjecture, they can prove prime tuples conjecture, and a bunch of other things too. But the method is very specific to function fields. But also many of these previous results here, these arguments can also be adapted to function fields, and there's some work, recent work of Clement, Mangro, and Teravainen that do that. Okay, but even k bigger than 4 and bigger is still open. Okay, so let me talk about how we've made progress on these Chowla conjectures, and it's basically an adaptation of the same type of ideas I mentioned at the beginning that gave it this new proof of the prime number theorem. In fact, historically, these ones came first, and then the prime number theorem proofs came a little bit afterwards, at least partially inspired by what happened with Chowla. So remember, Elvis inequality, which basically comes from Cauchy-Schwarz, gives a dilation invariance that if you take an average any function f, say log average, you can dilate f by a prime, and usually you get back the same average. And it's a nice application of Cauchy-Schwarz. Now it turns out that there's a variant which is a little bit similar. That if instead of dilating a function, you dilate a correlation. So if you take the correlation of if you take a function f and you shift it by h1 up to hk, and you shift it by multiples, you dilate the shifts by some prime p, then this correlation turns out to, for most primes p, is roughly the same as this correlation, where you dilate p, but you don't dilate the shifts. You keep the shifts the same. So this is not the same as Elliott's inequality because wait a minute. Actually, the way I wrote it, it is, I guess, because I made a mistake. Yeah. Okay, there's no p here. That's sorry. Okay. Yeah, if there was a p here, that would be Elliot's inequality. But yeah, the key point is that there is no p there. And then this is not just changing variable p n to pn. Yeah, so these two averages turn out to be the same for almost all p, but there's a much stronger restriction. So here for Elliott's inequality, any p which is a little bit less than say x to the epsilon would be okay. Here we actually need p to be less than log x to the epsilon. So that actually is a very annoying restriction. But we have this alternate variance approximation. And it's not proven by Cauchy-Schwarz. At least no one knows of a way to prove it by Cauchy-Schwarz. Instead, we prove it actually using entropy inequalities, using information theoretic methods. So let me explain this inequality. Well, the proof is a little bit more complicated than Elliott, but roughly speaking, and again, I got the same typo here. Okay. All right. Yeah. So okay. Yeah. I feel like I've Okay, the P's are not. I will fix the slides when we in the final version. There's something wrong with the P's, which I'm not going to fix in real time. Okay, but the reason why this is true is that if this is a bit okay. All right, yeah. If these two averages were not the same, all right, yeah. This statement doesn't actually follow from what I just said. So there is a typo somewhere, but what should happen is that the reason why the only way that these two averages can differ is if the values of this expression of this product depend somehow on the residue of n mod p. Because if they were independent of n mod p, then you could replace n by a multiple of p, and you would get back. All right, I have messed this up, unfortunately. I apologize. All right, okay. So yeah, this statement is not strictly speaking correct, but okay. What should happen is that if there is a discrepancy here, then this sequence here somehow knows about the value of n mod p. And in the language information theory, it means that there's some mutual information between the sign pattern. If you look at a certain sign pattern of a certain length, this function f, the sign pattern must, the starting point of the sign pattern must know something about the residue of the starting point mod p, where n is just some random number drawn from 1 to x. But on the other hand, all these residues, they behave independently of each other. So if you pick a random number n, you look at n mod 2, n mod 3, n mod 5, as long as your sample length is bigger than 2 times 3 times 5, all these residue classes are kind of independent. So all these residues, these random variables are kind of independent. So they share no information among themselves. They're independent, but they're all trying to share information with this other random variable. And the entropy inequalities prevent that from happening. But you can't have a random variable that shares information with a lot of different independent random sources at the same time. And so you can get a contradiction this way. But in order for this to work, p has to be less than log x. Otherwise, the Chinese remainder theorem doesn't apply. Although very recently, there was this very nice development by Helfgott and Matsui, at least for k equals 2, where they didn't use the entropy method. They used instead expander graph methods, and they were able to get past this barrier. Okay. Okay. Well, anyway, once you have this extra fact, you can use it. Right. So so we have this entropy approximation that these two averages are roughly the same. If you apply this Liouville function and you use the multiplicative property, this tells you that the correlation of Liouville at these shifts P1 H1 of PHK is related to the correlation from H1 to HK by this sign -1 to the k. So you can use it to control one correlation by another correlation. You can basically dilate the correlations by primes. And yeah, so if you do that, okay, and you can do it for any prime p, or at least most primes p, and then you can average in p. So you can replace a correlation by an average correlation where you get to dilate the shifts by a whole bunch of primes. And these double averages turn out to be more tractable. You have many more tools. We have many more tools to control a double average than a single average. For example, Cauchy-Schwarz becomes more useful for double averages than for single averages. Also, the circle method becomes more useful. So this is sort of the starting point to make more progress. So for example, if you are, so the simplest non-trivial case of Chowla, if you wanted to correlate lambda of n with lambda n plus 1, you can use these entropy methods to replace this with a correlation between lambda of n and lambda n plus p, where p is a prime ranging in some range. And this double average turns out to be very tractable by the circle method, which I guess there'll be a whole week of workshops on later in this program. And you can control, as it turns out, basically you can control this average by short averages of the Liouville function that you can control. So this double correlation by just correlations averages of a single copy of lambda on a short interval. It's actually, you have to add a few more terms in this, but this is the main term that controls this expression here. Fortunately, there is a very powerful theorem from multiplicative number theory that controls this. There's a theorem of Matamaki and Radziwi that tells you that there's a cancellation for these sums. They controlled actually any bounded multiplicative function. They understood what happens on averages on short intervals, and they can use that. And you can use that to control these are averages, and this is what gives you the k equals 2 case of the Chowla conjecture. Okay, how much time do I have? Let's see. Okay. All right. And you can use a parity trick to get the odd k case. If you have this average, you can use this entropy method to dilate the scale, the shifts by p, and you get a minus sign. Or you can dilate by you can use it twice, and you can dilate by semi-primes, and then you get a plus sign. But it turns out that both these averages can you can kind of compute them, and you can show that they're almost the same as each other. Primes and semi-primes have very similar sort of Fourier analytic properties, and so if you use a suitable version of the circle method, you actually need a higher order version, which involves no sequences and things like that. But you can show that the average over primes and the average over semi-primes is basically the same. But because you have the sign difference, you can combine those two, and you can show that these averages are close to 0. This should remind you of sort of how you prove the prime number theorem by these methods, which is sort of the k equals 1 case, but the argument actually works for all odd k. Okay, so we have in some sense half of Chowla's conjecture proven in the logarithmic average case. Unfortunately, the even case contains most of the interesting correlations, but we do at least have the odd ones. So for the even ones, we don't have the full conjecture yet. So the sticking point is we need a higher order version of this Matamaki-Radziwi theorem. So the Matamaki-Radziwi theorem says that on short intervals, lambda has small mean. Okay, so that we understand. But when you go to higher order, what we actually need is that not only does on short intervals lambda have small mean, we also need lambda to have small Fourier coefficients. So what we actually need, so let me actually skip this high order version because it's kind of technical, but the kind of things that we need are the following: that if you look at a small interval between n and n plus h, and for most small intervals, if you look at the Liouville function on a little window, and you take the worst Fourier coefficient of that function on the interval, so you correlate lambda with a linear phase, and you take the worst phase for every single interval. Even taking the worst phase for every interval, you should still get the k. This is called the Fourier uniformity conjecture. There are two parameters, x and h, and this should be true no matter what h is, as long as h grows to infinity. The smaller h gets, the harder this conjecture becomes, but we need h to be like log x or something smaller than log x is what we need for applications. Now, there's a more complicated version where you replace this linear phase by what's called a null sequence, but let me skip that. But roughly speaking, if we could solve this conjecture, we would pretty much settle. Well, okay. If you could prove the more general version of this conjecture, you would establish the log average Chowla conjecture and the log average Sarnak conjecture, and it would get lots and lots of applications. So this, I think, is the bottleneck. So if we can get if we can understand local Fourier coefficients of the Liouville function, then we can make further progress. So we've been trying to do that, and there's some progress on this conjecture. So if you put these, if instead of taking the worst frequency for every short interval, if you fix the frequency in advance, you move the soup outside, and you have a single frequency for all the intervals, then we can prove it. That I did with Kaiser, Matamaki, and Maxime Radziwi many years ago, and there's a similar thing for higher order, no sequences. but that's a much weaker statement. More recently, if h grows fast enough, so if h grows like some small power of x, and in fact, we can even do slightly better than a small power of x, then we can actually make progress. So we had a difficult argument to prove this last year, but then very recently, Miguel Walsh simplified it quite a bit. And it's now basically a 10-page argument. It's not too bad. And there's also higher order version. We're averaging over x. If you don't ask for almost all intervals, but you actually ask for all intervals, all short intervals, do you get a gain? We can do that too, and we get actually quite a good gain. But now the interval needs to be pretty big, about x to the 2/3. So that's a recent result of Kaiser Manaraki and Zhuangcheng Xiao. And in work in progress, we are extending these results not just to bounded multiplicative functions, but to unbounded multiplicative functions like the divisor function. Okay. So we can get h down to about x to the epsilon. If we can get h down to log x to the epsilon, we would get the Chowla conjecture. But there's this huge barrier in the way, unfortunately. Okay. All right, so let me tell you a little bit about Walsh's argument, Walsh's arrangement of this argument. So it still uses these sort of Elliott type methods, but with one additional input, which is quite nice. So what's the enemy? Okay, so suppose this local Fourier uniformity conjecture is false. So what that means is that for many short intervals, the Liouville function is pretending to be like a linear phase. That the Liouville function, so sort of the enemy is that you call this big interval from say x to 2x or something, and the Liouville function is sort of behaving like a Fourier phase on one short interval, and then a different Fourier phase on another interval, and then another Fourier phase. So it's somehow looking like correlating with a piecewise trigonometric function somehow. So if it somehow looks, so we want to show that lambda does not look like this, or does not correlate with that. But if it did, what it would mean is that for at many locations x, the Liouville function is behaving like a linear phase depending on some frequency. Okay, but the frequency keeps changing with x. So you've got some unspecified frequency which keeps changing. It's like some weird musical piece where at every time there's a different note, and there's some weird piece of music which the Liouville function is apparently playing. Okay, so we want to somehow get a contradiction out of this scenario, and the only thing we have available is this multiplicativity of the Liouville function. Okay, so the Liouville function behaves like a linear phase, okay, but on the other hand, it has a dilation invariance. Okay, so if you get number x, you divide it by p. Okay, so if at some location x, lambda is oscillating some frequency, okay, we also know that lambda pn is minus lambda n. So if you divide by p, lambda should also oscillate at a faster frequency, p times faster. Okay, that over on this other interval, this frequency should, it's scaled by p, it should oscillate p times faster. So, and you can make this rigorous using this sort of Elliott inequality type business. So you also have this frequency over here. So now this is it. Okay, but on the other hand, we also expect over here lambda should also oscillate at alpha x over p. Okay, so lambda is oscillating by two different frequencies. So these frequencies we would expect at least some of the time they should oscillate. They should correlate with each other. They should be somehow constructively interfering. And so what we see is that there should be a relationship between the dilated version of this frequency and this frequency here. That in order for this piece of music to be multiplicative, there has to be some relationship between the frequency at one location x and the frequency at some other location x over p. So we get a certain equation a functional equation, if you wish, relating frequencies at different times. And so, so now what you need to do is you need to solve this equation. Okay. Oh, and there's one other equation which is relevant, that the music can't change too much over short periods of time. That if you have two nearby points x and x prime, and lambda is pretending to be one frequency on one interval, and it's sorry. And it is pretending to be a different frequency on some overlapping interval, then in order, if you want these two frequencies to be compatible, you would also expect these two frequencies have to be close to each other in a certain sense. So actually, there's these two equations that you kind of need to be consistent with this bunch of frequencies correlating with some multiplicative. Okay, so right, so you end up with this combinatorial question. All right, what kinds of frequency assignments x maps to alpha x can you find which are sort of locally stable, that they don't vary very much when you take small perturbations, and also they have this sort of multiplicativity that if you dilate x by 1 over p, the frequency should increase by p, at least mod 1. Okay, so you want to solve these two equations. Now, it turns out that there's sort of an obvious solution to the system of equations. Okay, hang on, my computer has frozen. That's not good. Oh no, okay, there we go. All right. So here are my two equations. So there's an obvious solution actually, that if alpha, the frequency varies inversely with the position. If the alpha is like t over x plus some error, and t is not too big, then you can check that a frequency which oscillates inversely to position obeys are compatible. And actually, what this means when you have this inverse relationship, if you actually Taylor expand it, it means that all these little frequencies are actually they're actually modeling a multiplicative frequency. So if you take the function entity it and you look at it on short intervals, locally it looks like a plane wave, and the frequency actually turns out to be t over x if you do the Taylor expansion. It's basically because the derivative of t log n is t over x. And so yeah, if alpha looks like this inverse proportionality, then all these little Fourier phases are actually correlating into one big multiplicative character, entity it. And saying that lambda correlates with all these little factors is saying that lambda correlates at least locally with entity with this multiplicative character. But the theorem of Matamaki and Matsui that I mentioned earlier actually shows that this doesn't happen. And so this is how Walsh and everyone else gets a contradiction. So so the main thing you need is sort of an inverse theorem. Okay, so we know that that this type of frequency assignment solves these equations, and the hard part, the remaining hard part, is the inverse step, saying that any solution to these equations looks like this. So it's a bit like these Riemann theorems that actually Larry mentioned in the previous lecture. And so so to do this, okay, so if we didn't have this mod 1, then you could just iterate this and divide by p and so forth. Okay, but this mod 1 prevents us from dividing by p, and that's very annoying. Yeah. The other thing is that we don't have many p's to work with. P is actually kind of small, so we can connect x to x over p, but that's a very sparse graph. So there's a graph underlying this. Like this x lives like in some interval like x between x and 2x, and then x over p lives in some smaller. Sorry, I'm having some slight technical difficulties with my computer. Yeah. Okay, so there's actually implicitly a graph in play where you connect points x to quotients by various primes, but it's a very sparse graph. Most points are not connected to each other by a short path, so there is some structure here, but it's sort of local, not global. So so Walsh had this very nice idea. So I'm running out of time. And I'm also running out of apparently computer memory.
No worries, you can have a few minutes more.
Yeah, there we go. All right. Okay, so yeah, so he has this idea which he calls contagion. So you have a frequency function. You have some frequency function which lives at scale x, and you have another frequency function which lives at scale x over p, which I also call alpha, and they're connected together by these various equations. And he's able to synthesize these guys together, all this data. Okay, and he can create a new function at a bigger scale, x times p, which he also calls alpha. Okay, and he can sort of extrapolate the structure to a structure at a much bigger scale, and then and you can keep iterating. Oh, gee, this is annoying. Sorry, my computer is not liking me drawing on the screen. Okay, you can keep iterating this to a really large power, and you can create all these new frequency functions that are all connected to each other by many connections. And the point of doing this is that if you do this enough times, now I want to change my color. Let's see, there we go. If you do this enough times, you can pick one point at the top. Okay, such that if you look at all the descendants of that one guy at the top, you can start hitting almost every point on your original function is sort of a descendant of one big ancestor. You're sort of extrapolating a big family tree. It's like you sort of piecing together some sort of genetic history of all the structure, and you can find a common ancestor to pretty much everybody from your original function. And so you can describe the entire frequency function in terms of one piece of data. And this is what he uses to actually get the type of solution, the solution structure that he needs. So this is the main idea, and so the key step is this extrapolation, just to extrapolate the data just one step. Oh, and you can see that this is why, by the way, you need a condition like this to get so that you can do this in some bounded number of steps. Okay, so right, so the so the key step is that all right, let me do one last picture. Okay, so here's x, here's px, here's x over p. Come on. Okay, so if you want to work out what frequency you need to assign to this new scale, you can divide by one prime p, or you can divide by another prime p. Okay, and you can look at all the different frequencies here, and you want to synthesize all this data together to form one single frequency here. And what you do is that use the fact that these frequencies are compatible because they both divide to the same. Yeah, so basically you use a lot of parallelograms that are present in your graph that these frequencies talk to this frequency here, and using these three frequencies, you can predict what frequency should go here using, okay, so there's a bunch of equations that you need to solve, but because of the Chinese remainder theorem, it turns out knowing these three frequencies, they sort of uniquely determines pretty much what frequency you need to put over here. And then you can just keep repeating this for all these other parallelograms. You need to check that they give sort of compatible information, that they all predict sort of the same answer for what you should put here. And this you can do from elementary number theory. And the key fact ultimately is the fact that that fractions of 1 over A over P and fractions B over Q are kind of separated from each other when P and Q are different primes. So that's a very classical fact in number theory, and that's kind of what makes this this extrapolation step work, and it iterates quite nicely. So that's sort of the state of the art of where we're at right now. So just to summarize, I have my final slide. If my computer lets me advance one more slide. So right now we now have a pretty good understanding of what the Liouville function is doing on short intervals, as long as the interval is at least h3 epsilon. That makes the graph, this graph I've been drawing, kind of bounded diameter, that any 2 points can be connected in bounded time, in bounded length. Once you go much beyond that, it gets much harder to make progress. I mean, maybe I think it looks like the methods can be pushed to exponential. Come on. Exponential log x to the 1 minus a small constant. But that seems to be the limit of what we can do by these graph methods. I think at some point we actually have to start using large primes. This is about the most you can squeeze out of just using small primes. Okay, but so this is gap. But what we would really like to get to is like log the epsilon, because that's where all the really cool applications sort of so yeah, you basically get all the Chowla and Sarnak conjectures, at least with log averaging. Yeah, so we are missing one extra technique. I think we have sort of 2 out of the 3 key ideas needed to solve this problem, but we're missing a third. And the third is something we need to bridge the gap. Yeah, so there's this barrier at log x in particular, which looks very formidable. And we have very few results that actually cross this barrier. The mathematical Radzivil theorem is one of the few ones that does, that we can actually control things on short intervals, even shorter than log x, by mathematical Radzivil, but that relies very much on multiplicativity, and we haven't been able to extend that to these other settings. And the Helfgott-Radzivil stuff, that may possibly do something with k equals 2, although so far, yeah, although that relies very much on graph theoretic techniques. The analog for higher k would need hypergraph spectral theory, which doesn't really exist. So that I think is also going to be a challenge. But anyway, that's where we are right now. So I guess I will stop. Sorry for going over time.